In this video, I will show you how to convert the two-dimensional coordinates of a mouse to three coordinates of real object in the world space. As you know, the mouse has two coordinates of x and y on the screen, but we want to select a three-dimensional point, member, or object in the world space. I will show you we can do it by a series of transformations. A three-dimensional coordinate of a world space object can be converted to a two-dimensional coordinate of a mouse or a screen space. I will show you how we can convert a three-dimensional point to a two-dimensional point on the screen using a numerical example and apply it to the code of a graphical program. Also, I will discuss word space, eye space, homogeneous, and clip space, as well as viewport or screen space, along with view metrics, projection metrics, and perspective metrics. To convert from word space to eye space, we utilize rotation and translation matrices. Additional, I will discuss some coding example related to our topic using the OpenTK library. Here are our main references on this topic. They are excellent resources and I highly recommend reading or watching them carefully. Every research must have a research question. So what is the question of our research? The question of our research is, how do we convert the two-dimensional coordinates of the mouse in the view space to 3D coordinates of the real objects in word space? The computer screen is a two-dimensional space. When we click on the screen, we get only the x and y value of the screen pixels. However, we aim to select a three-dimensional object in our scene or word space. What is our solution? It can be achieved through a series of transformations of a three-dimensional coordinate of objects in word space to convert them to the two-dimensional coordinates of the mouse or screen space. Our 3D object is a structural and moment-resistant frame of a concrete building, and we want to convert the coordinates of a base point of a column with coordinate of 5.3200 to two coordinates of the screen space. This is the ConkDetailer software, which can generate structural drawings. On the right side, we have a three-dimensional model of our building. I've displayed the mouse coordinates on the text property of the form, allowing us to observe the mouse coordinates as we move the mouse. One application of mouse picking and converting to word coordinates is the selection of objects in the three-dimensional word space using the mouse. For simplicity, let's convert the coordinates of this point, which has x, y, and z coordinates equal to 5.32, 0, and 0, to mouse coordinates of ex and ey in the screen space. The transformation path is depicted in this slide. We begin with the coordinate point in word coordinate space and transfer it to the eye coordinate space using the view matrix. Next, we convert it to homogeneous coordinate space using the projection matrix. In the subsequent step, we transfer the coordinate to the clip space, which is essentially a two-dimensional space. Finally, we convert the coordinate to viewport or screen space, which represent the mouse space. The first step of our transformation involves converting the coordinates of points from word space to eye space. This essential transforming the original eye coordinate system to the word coordinate system. Essentially, we aim to determine the coordinates of point 1 when measured from a new coordinate system with its origin located in the eye point coordinates. The eye point has a word coordinate of -L, L, which L equals to 26.71 meter. While the specific value of L is not crucial, it represents the maximum dimension of the model. The length of the OA and OE can be calculated using the Pythagorean theorem, resulting in 1.41 L and 1.73 3L respectively. The tangent of the angle of AOE can be found as AE over OA, which is L divided by the square root of 2 times L. Thus, we can determine the angle of AOE to be 35.26 degrees. To transform the I point to the origin coordinate of the space, we first apply a z rotation equal to 45 degrees to the I point to bring it to YZ plane. The z coordinate matrix is depicted below. The next step, we should apply an x rotation equal to 54.73 degrees to the I point to bring it to the z axis. The x rotation matrix is depicted below. In the final step, we should apply a translation in the minus z direction equal to 46.26 meters to the I point to bring it to the origin of the space. The translation matrix is shown below. We can combine the three above transformation into a single transformation matrix by multiplying T sub T by T sub Rx and then by T sub Rz. The single combined transformation matrix is called the model view matrix. Therefore, we concatenate the three matrices and multiply them to obtain the view matrix. This is the view matrix. The matrix combination is a powerful method to streamline calculations applicable not only to graphical transformation but also to matrix structural analysis and finite element method. Now we can apply the view matrix to the word coordinates of point 1 to obtain the I coordinate of point 1. The coordinates of point 1 in I space are depicted in these figures. In the left figure, the z-axis of the I-coordinate system is perpendicular to the image, hence only a dot is visible for it. The distance of the x and y coordinates with respect to the I-coordinate system are also illustrated here. The right picture presents the I-coordinate system from a different perspective. Here, it can be observed that the z-coordinate of point 1 with respect to the I-coordinate system is minus 49.3 meters. The purpose of transforming the word coordinate system to the I-coordinate system is to bring the z-coordinates of all points close to each other in the I-coordinate system. Consequently, only the x and y coordinates are significant in the I space. Thus, the three dimensions of a point in word space are converted to a two-dimensional point in the I space. This is like viewing a building from street view versus from a high-level point. From the high vantage point, the z-coordinates of object are closely packed, resulting in the perception of building as two-dimensional object with x and y coordinates. In the next step, we need to convert I coordinates to homogeneous clip space. Essentially, we want to map all objects in the frustum space to a cube space with the dimension of plus z and minus z, which z represent the distance from the I to that point. This transformation matrix is known as the projection matrix. The frustum space is the region that camera or our eye can see and all objects are located inside of it. It's defined by a near and far clipping plane perpendicular to the z-axis, the field of view angle FOVY, or camera angle, which is the angle between the upper and lower planes of the frustum space, and finally by the respect ratio, which is the ratio of the width to height of viewing window. This is the perspective matrix, which is a combination of scaling and translation matrices. The aspect ratio is the ratio of the width to height of the form, which is 699 to 790 pixels or 0.8 3.96. The camera angle, theta, is 45 degrees, and its relationship with the focal length, f, is tangent theta over 2, which equals 1 over f, and is 2.41 in our case. The ratio of f over aspect is 2.69. We take the near and far plane distance from origin 1 and 10,000 meters, respectively. And finally, we can calculate all items of the perspective matrix. The coordinate of point in the homogeneous clip space will be calculated by multiplying the perspective matrix by the coordinate of the point in the eye space. Remember, our entire visible model is transferred into a cube with a length of 49.33 meters. In the next step, we will transform the homogeneous clip space into a clip space with a length of 2. It can be done by dividing all coordinates of the point to w equals 49.33. Therefore, the x and y coordinate of point in the clip space show the distance of point from x and y axis into our form, such as depicted in this figure. The x coordinate of our point is 0.2053 and y coordinate is 0.1059. The z coordinate of point is perpendicular to our view plane of x, y, so we are not able to see it. It is needed because we use it to find how much this point is close to the eye or camera. This is important when we want to select the nearest object between several objects that are in the same direction by mouse. In the final step, we should transfer clip space to viewport space, which is in fact screen space, and we have access to it by mouse coordinate. The unit measure of the screen is pixels, with the origin in top left of the screen or form. Therefore, with a simple equation, we can convert the coordinates from clip space into viewport space. The width and height of the form are 699 and 780 pixels. Thus, the x and y coordinates of mouse will be 421 and 349 pixels. Based on the above algorithm, we can define a simple subroutine to find the mouse coordinates by entering the word coordinates of a point. I have used OpenTK library and VB.NET, but of course the algorithm can be implemented by other libraries and languages. First, we should define our projection and model view matrices. Then multiply view matrix and projection matrix to our coordinates point vector to transfer word space to eye space, and then the homogeneous space accordingly. In the next step, we can normalize our vector by dividing its component to the last component of the vector and transfer homogeneous clip space to clip space. Finally, we can transfer the clip space to viewport space by using two simple equations. I have developed a small subroutine to find mouse coordinates from word coordinates based on the above algorithm. To understand how it works, I will call it from mouse down click event with the coordinate of desired point. When I click the mouse button, this sub will be called. Let me run the program and open a file. Now, as I click the mouse button, my subroutine will run. The coordinates of the point are 5.32, 0, 0, and 1. These commands will retrieve the projection and view matrices. In this command, I have multiplied the view matrix by word coordinate of the point. Let's examine the view matrix members. As you can see, they are the same as our hand calculations of the view matrix member, but by default, they are transposed. Let us continue to run. Now we have the eye space coordinates of 3.76, 2.17 minus 49.3 and 1. Press the continue button again. This command multiplies the projection matrix by the I space vector. So we have the homogeneous vector with the same value of 10.14, 5.23, 47.38, and 49.33 as the hand calculations. In the next step, we have clipped the space coordinates of 0.2053, 0.1059, 0.9595, and 1. In the final step, we have viewport space coordinates of the mouse in pixels, which match the hand calculations of 421 and 349.